All right, guys, sorry again about class today. I come to work and then the school called and my daughter was sick. So we are going to start with chapter 1.5 or section 1.5 and talk about matrix algebra. So basically what we're going to do in this section is we are going to look at like what are some, so we had done the kind of arithmetic with matrices before. So now we're going to look at, well, what are some of the general properties that we know from matrix arithmetic, and we'll actually prove some of these. So we kind of saw this in class that when we did A times B, it wasn't equal to B times A. So that's the stuff we're going to talk about today. What are things from the real numbers that we can show are the same when we're using matrices instead of numbers? And then what are the things from the real numbers that are not the same when we have matrices instead of numbers? So that's what we're gonna kind of look at. So first, a couple things. First thing we want to talk about is this definition of the zero matrix. So in the real numbers, zero is quite important, right? It's a number that's really important to us. We care about zero a lot. It's the additive identity, which means if I add it to any real number, it stays the same, right? As opposed to one, which is a multiplicative identity, because when I multiply any number by one, it stays the same. So the zero matrix, right, we're going to go ahead, is just a matrix which has zeros for all of its entries. And we will, so every entry is zero. And we'll denoted just a zero. And for this guy to show that it is a matrix, you know, it'll be a little tough. Well, I'm not sure what I'm going to do here. So we'll just, you know, in context, we should be able to see that it's a matrix, but I might even just put a bar over it or something to make sure you understand that it's a zero matrix and it's not a scalar and it's not a vector, right? Not a column vector. Okay, so we can denote the zero matrix, and your book does this. Ooh, look at that, makes that a really pretty zero. This is the software music for this. So the zero matrix, if we put a little m and n, this is going to be a zero matrix of size mn. So that will help too, because we won't always write it out of size m by n. So for instance, like if I say 0, 2, 3, then that's a zero matrix of 2 rows and 3 columns. Remember, that's not 0, 23, that's 0, it's 2, 3. I know, that's kind of weird. Good, all right, so some properties of matrix addition that we're gonna start with, and this is stuff that you're used to because you're used to working in the real numbers for the most part, which is a good place to work. But we also want to look at, remember, we're not dealing with the real numbers anymore. I'm actually going to call this a theorem because we're going to prove a few of these. So theorem, and we'll just put properties of matrix addition. So we want to know, like, what are some things we know we can do with matrices? And let's talk about it now so we don't have to prove this when we want to use this eventually, right? So let's let A, B, and C be matrices of size mn. So we know that's m rows and columns. So if that's true, then, so notice, this is kind of important. We know that A, B, and C must all be the same size, okay, for all of these properties to hold. So property A, we're gonna say that A plus B is equal to B plus A. And I know that seems trivial, but it's not when we're dealing with matrices. Again, we had seen in class that, we saw in class, wow. Oh no, grammatically, that's correct. That A times B is not B times A. So we're dealing with a whole new system now. It's kind of exciting. You know, you've grown up learning arithmetic with real numbers, and now we get to learn a whole new arithmetic. It's new and and it's exciting. Sorry about that. Okay, part B, or our second property. But I can add two matrices together and then add the third matrix. So I can add A and B first and then add C, or I can add B and C first and then add A, right? So a couple things here. This is called the commutative property, the one above, right? Commutative property, and this is the associative property. I can associative two matrices together, and then the third, or I can associate the other two, and then the other. And then the other thing that we can, that is true, is that A plus dot 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 plus A. So if we have K of these, okay, then this is going to be K times the matrix A. All of these, we'll prove a few of these for you, but all of these really are just resulting from the fact that what is the definition of matrix addition? Matrix addition is adding component-wise. So the way we prove this, is we take A plus B and we show that we add component-wise, and then inside the components, just like when we proved that U dot V is V dot U, and then we just switch those components and rewrite it then as B plus A. So that's how we'll do that. All right. D, there exists a zero matrix. So OMN, such that, so ST, right, A plus a zero matrix equals A. So that's what I was talking about, that there exists an additive identity, that if we add 0 to the matrix, then it just keeps it the way it is, it stays the same. Okay, so that's an additive identity. We also have what we call an additive inverse. So the other side of that is that there exists a matrix. We're going to denote it negative A, such that if I take A plus that negative A, then we get the zero matrix. And realize that that 0, right, is going to be the zero matrix. Okay, so please understand that that's not a number. That 0 right there is my zero matrix. Maybe I'll get in the habit of kind of bolding that a little bit. And again, this all comes from component-wise when we're looking at this. So this is what we call the additive inverse. The additive inverse, as opposed to a multiplicative inverse, is what do I multiply A by to get 1? Okay, so an additive inverse. And we don't always know, we're going to see that for matrices, we don't always know if there's a multiplicative inverse, but there is always an additive inverse, meaning it's a matrix that I would add to another matrix to get the zero matrix. Okay, so let's prove some of these. One of these, I don't think we need to go through too many of them, but let's just prove A. Okay, so I'm going to prove A. So now we need to do this in the most general way possible. That's how you do a proof, right? So let's get the most general form of our matrix A, which we've seen many times now, right? This is my general form for matrix A. And let's let B be this matrix, B11 dot 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 to BM1, because it's an M by N, B1N to BMN. Okay, dot, dot, dot. So what do I want to show? So remember, if we're going to prove something, and in this class, we're going to prove stuff. So, sorry, you're going to have to get used to that a bit. So what am I going to show? I want to show that this is true, correct? But what I need to do, you have to make sure you start off with one side and then show that it equals the other. So I'm going to go ahead and start off with the left-hand side. It really doesn't matter which side I start with. Okay, just need to pick one of those sides. Sometimes it does matter. In this case, it's not going to. So I'm going to go ahead and say, okay, let's take A plus B then. So we know that if we take A plus B, right? So we'd have A11. This is going to get a little monotonous. That's why I'm not going to prove all of these for you, because it was just kind of, I wouldn't say boring. It's just a bit tedious. All right, and then we'll add the B. So B11 dot dot dot. BM1 dot 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 B1N to BMN. Okay, so now we know we add matrices component-wise. So this is where the strength of your proof is. So the strength of your proof comes from, really when we get down to it, when we add these guys, the components themselves are real numbers. And we know that real numbers are commutative, right? Oh, whoops, got a bit ahead of myself there. A1n plus B1n dot 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 A. So you see how this can be kind of time consuming, which it already is kind of. All right, but this is how a proof goes, right? You don't complain, you just, well, you can complain, but you still have to do it. So now here's where the strength is. Again, I'm going to take each of these components right here. Those are real numbers, and I know that real numbers are commutative, so I can rewrite this as B11 plus A11, right? Dot, 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 BM1 plus AM1. And you could maybe do this a little bit differently. And then we get over here. Sorry if this video seems a little disjoint and not flowing super well. It's because my children keep coming in because my oldest is home from school, so you might even hear them out loud. All right, and so what is all this though? So now notice what we have. Well, all of these components right here are B, and then we have, of course, these components right here are from our matrix A. So what is this? This is B plus A. Done. So that was pretty easy to show that. And that's what we would do for the rest of these. And I'm going to have you prove some of these in your homework. But that's how you kind of show that all of these are true, is you just kind of work with them component-wise. And I hope you can see that that's pretty easy to see. And I'm not going to actually do a whole lot of examples with these. I think we'll just do the fun sheet together. Or I want you to work on the fun sheet, maybe bring it with you on Tuesday. Because they're pretty simple to see. We just add and subtract component-wise, and we worked on that in 1.4. So look in your book. I would, if you want an example of this, I'm going to let you do this because I feel like you're there. You can look at example 1.22 on page 61. So I encourage you to go and look at that example and copy it into your notes. But I think you'll see it's pretty basic. You're just adding components. Okay, so all right, so let's move on. We're just, sorry, these are kind of a lot of theorems in this section, so maybe this is a good section for us to just have had on a video. But let's look at some properties of, we're going to talk about matrix multiplication here in a little bit, but what we're going to look at first are properties with just scalar multiplication. Okay, so theorem. All right, so now we're going to look at scalar multiplication. And we had some similar things like this when we talked about vectors, I believe. I might be getting that confused with Calc 3 because I get these all confused a bit. But let's let A and B, obviously, be m by n matrices. I'm going to get some shorthand for that eventually. Maybe not in this lecture, but I'm just lazy enough that I don't like writing that all the time. And then let's be matrices and let C and K be scalars. Okay. Okay, so if that is true, then we have the following properties. So the following properties are true. So basically I have an associative like property with these scalars. So I can multiply two scalars and then multiply it by the matrix. Or I can multiply the matrix by a scalar and then take that resulting matrix, right? This would give you a matrix right here, and multiply that by a scalar, okay? Then part B, I have basically a scalar distributive property. So, I was thinking in Calc 3 we did this when we talked about cross product. Kind of similar. Not exactly the same, but similar. So I can distribute a scalar. Again, if you were to prove all of these, you're just going to prove it component-wise. So you're going to go in and you're going to multiply each component by that number or whatever you're doing, and then you're going to factor those out. I encourage you to read that. This is on page 62 of your book. So on page 62 of your book, it goes through and it proves part A for you. I'm just not going to do that, prove C, because I'm going to have you guys do some of this in your homework. See, I could make you do it. And then we can have a distributive property when it comes to two scalars and one matrix. All right, and so I hope you'll look at the proof of that. That proof is on page 62. Okay, and I think you'll see that it's pretty easy to follow. Okay. All right, so I'm gonna go ahead and for some examples of those again, I would look at example 1.23 on page 63. I think those are pretty, they're really just arithmetic. That's the only reason I'm not really going over this with you in detail, is that it's pretty much just arithmetic. Okay, all right, so now here's where we get kind of interesting. So we're going to be talking about properties of matrix multiplication, okay, and we're going to kind of look at different ways to think about the multiplication, and then that will help us figure out there are some properties about multiplication, but the commutative property isn't one of those, okay? So let's talk a little bit more about what it really means to multiply two matrices. And we've done this before, or we talked about this in class, but let's look at this when we look at it very generically. So recall if I had, and we can show this pretty easily, you know, if I had 1, 2, 4, 1, 3, 5. So let's remind ourselves what it means to multiply two matrices. So this is a 2 by 3, right? And let's say that B is 3, 1, negative 1, 2, 0, 4, or something like that. And this is a 3 by 2. So we had talked about how we have to have the number of columns of A must equal the number of rows in B. So we could multiply these two together. So A times B. Now technically, what does that mean, right? We're going to take the first row of A and basically do the dot product of it with the first column of B. And so it's hard to show in this, but I would get 3 plus 4 minus 3, which is 4, I think. So I do the first row, right, and first column, okay? So now I'm going to do the first row with the second column. I'm going to basically do a dot product. So 2, 0, and 12, I believe, is 14. So that's going to go right here. Now I'm going to move on, recall, to the second row, first column. That's going to go right there. I got to get rid of all this. And let's see what I get. I'm sure I'm making mistakes. I'm confident I'm making mistakes. 6 and 1 is 7, minus 5 is 2. Okay, and then if I do the same thing for the last term here, second row, second column, I would get 4 and 20, which is 24. So that's AB. Now if we did BA instead, so BA, I would have 3, 1, negative 1, 2, 0, 4, right, times, and I can, there's a reason I did a 2, 3, and a 3, 2. I know I can multiply them, right? So let's see what we get here. So again, I'm going to do the same thing, except I'm going first row in B and first column in A, right? So now I'm doing the same thing, but it's going to be a little bit different because B is going first. So I have 3 plus 4 is 7. Again, first row, second column now would be 12 plus 2 is 14. And then first row, third column, 9 plus 10 is 19. And now I go back down to the second row, right? And then the first column. 1 and 0 is 1. Then 4 and 0 is 4. Well, it's always going to be 1, 4, and 3, right? Because that 0 right there is going to cancel out that second term of the column. And then finally, I'm going to do the third row, right, with the last, with all of the columns. So negative 1 and 8 is 7. Negative 4 and 4 is 0, and then negative 3 and 20 is 17. So clearly, the whole reason I went through all of this is clearly this matrix and this matrix are not equal. So we can see that one of the properties we will not be putting down with matrix multiplication is that AB equals BA. Absolutely won't happen, okay? All right, some notation that might be useful for us when we're talking about matrix multiplication, especially if we're going to prove anything. This might be a little bit easier to prove stuff if we're going to use this multiplication. And this is what we've already been talking about. But let's look at our matrix A. I'm going to do a few more terms than I normally do. So I'm going to do 1, 1, 1, 2, 1, n. I'm going to do A2, 1. A2, 2, dot, 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 to A2n. Then we're going to go down. Let's pick out a middle column really quick. And we'll just do let's take the jth, or the ith row. So dot, I'm going to do I1, A, I2, dot, 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 right, dot, 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 A-I-N, okay, and then I'm going to come down. This is still going to be AM1, AM2, dot, 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 dot. Do you like that I say that? Dot, dot, dots too? Okay, and now let's multiply this by the same thing with b. b11, b12, dot, 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 b1n, b21, b22. What I'm looking for here is I kind of want to see, oh, I'm sorry, I wanted a J in there. I was getting a little too ahead of myself. We want to see if there's an easier way to describe this matrix multiplication. And basically what I'm showing you is, you know how I'm saying you take the first row and dot it with the second column, second row and dot it with the third column or whatever. That's basically what we're trying to, this is what I'm trying to get at here. It's just taking me a while. So let's say that this is now remember, oh, R, I'm sorry, we don't necessarily have N's. Let's do R here, because what if let's let A be an M by R, and let's let B be an R by N. There we go. I'm sorry about that. R, 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 R. Okay, so this right here is an R by N, so this is going to be, first it's going to be a B, and then R1, dot, dot, dot. Let's just take the jth row. So this will be 1J, B2J, dot, 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 BRJ, dot, 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 B1N, B2N, B, and then we have RN, right? Okay, so let's look at what it means to multiply this matrix. So this is going to be the notation that we're going to use to specify this. And I really, actually, I haven't really seen this notation before, and I really like what your book does here. So this is what they call, this is AB11, right? Because this is going to be the matrix AB. This is going to be the first entry in the matrix AB. This is going to be, right, for AB, that matrix, and then I'm going to have the first row jth column here, dot, dot, and this will be the matrix AB. This will be the first row nth column, because remember, what is AB? AB is going to be an M by N, okay? And then this will be AB, that's the matrix. 1, 2, dot, dot, dot. This would be AB 2J, dot, dot, dot. This will be AB, I'm sorry, 2N. I messed up there. That, right, should be 2, 1, okay? Yeah, and then, oh, there's a mistake in your book. I should email them, tell them that they have a mistake there. That's not a huge deal, though. And then if we go to the ith row here, I have I1, dot, 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 A, B, I, J. And this is the one we're going to look at, that A, B, I, J, dot, 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 dot. And then I'm going to have A, B, I, N, right? Okay, and almost done here. We're going to have A, B, we're going to have an M by N, so M1, dot, 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 AB, it's still going to be M, but in the jth column, dot, 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 dot. You're going to have like nightmares of my voice going dot, 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 dot. Okay, so here's my AB matrix. All right, so how do we get this term ABIJ, right? Well, this is exactly, so if we look back at this guy right here, right? So this one right here was the first row of A, so it was the first row of A, so I'm going to call that A1, dotted with, right, the first column of B. And then this row, this term right here was the first row of A, dotted with the second column of B. This right here, what was that too? That was the second row of A dotted with the first column of B. And this number right here, this 24, how do we get that? That was the second row of A dotted with the second column of B. So that's exactly when I look then at this ABIJ. So that ABIJ, what must that be? This ABIJ we have seen, which is really cool that it works out this way. This is just going to be the ith row, right? So this is the ith row of A, right? Dotted with the jth row, or excuse me, jth column of B. And that's what that matrix multiplication is. So if I asked you on any matrix, let's say you have a 5 by 6 matrix, right, that you got from maybe a 5 by 2 times a 2 by 6. If I asked you to find the third row, second column of that matrix, you would be able to take the third row of A dotted with the second column of B and find me that term. All right, so that's what's going to help us with this. So what would this be then? That would be the ith row of J of A, which is going to be AI1, AI2, AI3. So I'm going to write this as actually a row vector, AIR. Okay, and then because we know that's how we dot vectors, right? We've talked about dotting vectors before. So, whoa, sorry about that. That's a row vector dotted with a column vector. So this one's going to be B1J, B2J. Yeah, my columns stayed the same, all the way to BRJ. Okay, and then you just dot those. So if you dot those, then we see we get AI1 dot times B1J plus AI2 times B2J plus dot 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 plus AIR times BRJ. And then if you've missed, which I know you have, if you've missed a little bit of sigma notation in your life, if we wanted to write this as sigma notation, we said starting at k equals 1 up to r, we could have AIK times BK. J, right? That would give us that I plus J term. Okay, good. So this notation can be useful because if we wanted to prove something, we would be able to use this to prove what we have. Or let's just do an example. There's an example in your let's do an example like I said. So let's say that we have A. Let's say that A is I don't know, let's just do 1, -1, 2, 3, 1, 0. I always try and do like lower numbers because I don't want to deal with high numbers. -1, 5, -2. So let's look at what this is. This is a 3 by 4 matrix, right? And let's say that B is equal to, so I have to have 4 rows in this one for sure, right? So 4, 3, I'm getting lazy, 2, 1, -1, I don't know, 2, 1, -2. Okay, so this is a 4 by 2. So I know I can matrix these. I can multiply these. I can do A times B. I cannot do B times A, right? Because I don't have the right dimensions. But if I want you to find, let's say I want you to find, so what do I know? This is the result, AB, right, is going to be a 3 by 2. So let's find the second row, third column of AB. This is the power of that notation, okay, is that I can find the second row, third column entry of the matrix AB without actually having to find AB. And so how do we do that? We take the second row of A, which is -1, 1. This is called a row vector. I think you saw that when you finished up your reading, I believe, for 1.3. This is the second row, and then oh no, what did I do here? There's not a third column. Sarah. I'm sorry, it's a 3 by 2. Oh, Sarah. All right, so let's find, it's a 3 by 2, second row, second column. Second row, second column. So I take the second row of A, I dot it with the second column of B. And now I just dot that. I'm going to take -1 times 1, which is 1, plus 1 times 2, which is 2, plus 1 times 1, which is 1, plus 5 times -2, which is -10, right? And so what does it look like we get? We get -6. So I know that that is going to be this entry in the second row, second column of the matrix AB. Okay. Cool. I know I'm getting kind of long here. So let's go ahead and write down some properties of matrix multiplication. You can look at the other examples in your book. That will be pretty easy to see, I think. They're pages 66 and 67. I just did an example similar to the one on 66. But let's go ahead and write down this next theorem or proposition. Okay, and these are the properties of matrix multiplication. Properties of matrix multiplication. All right, so let's look at some of these properties. So some of these are going to be okay. That will make sense. Some will leave out that, you know, like the commutative property. So let's let A be, so we're going to be a little bit more generic here on the size of A and B because it has to work for the multiplication. So we'll say B matrices of appropriate size. Okay, a lot of books you'll see them actually force them to be sizes. Well, not force them to be sizes, but be like an N by R, an M by R, or whatever. But I kind of like this, of appropriate size. So the following operations can be carried out. Or I'm going to say so that the following operations are defined. Okay. So if that's true, then here are some properties of matrix multiplication that we know. So first off, we do have an associative property of matrix multiplication. That one's okay because we are not moving around the order of the matrices. Okay, so that's why the associative property is all right when we're talking about multiplication. So this is the associative, okay? I do have a distributive property. Again, I'm not changing the order in which these are being written, so I can actually associate, or I can distribute matrix multiplication. That is okay as long as I'm not rewriting the order, right? That's what we have to be careful about with matrix multiplication. So notice I have the distributive property. I have it on the left and the right. So you'll hear me say sometimes, and we'll get into this, I think your book uses this notation, we'll say like right hand multiplication or left multiplication. That's important to know because it matters, right? So notice this one here is a left multiplication and this is right multiplication. And we have to define those separately, and we have to say that those exist separately because of and your book says the left distributive. This is left, okay? And this is the distributive, and that's right. Okay, it does matter. Because matrix multiplication is not commutative, all right? And then finally, when we multiply by the zero matrix, that's the only one that has some commutativeness happening, is because 0 times anything is 0. So I actually can commute 0. And that's the only matrix where that's guaranteed. And I'm not saying you can't find me two matrices that will commute. You could find me two matrices maybe that commute. But what I'm saying is that that can't be true for all of them. So I'm not going to go through a proof on this, but I would like you don't have to write this in your notes, but I would like you to review, just read through it, the proof of B on page 67. Okay, so again, you don't need to write it in your notes even, but it's important for you to start understanding how mathematical proofs like this work. So go ahead and read through that proof. See if you understand it. Maybe even make a note of a place maybe where you don't understand it, and we can talk about that in class. Okay. Oh my gosh, you guys, this is getting kind of long. So what I'd like you to do is go ahead and copy example 1.2.6. You could even pause the recording right now on page 68 into your notes. Okay, so again, a lot of it's just the multiplying of the matrices and showing that some of these work. Sometimes they might not work because they don't have the appropriate size, but please review that example on page 68. Okay, and then we are almost done here. Okay, we're getting there. I'm sorry. This is kind of a long section. All right, and then the last thing that I want to, well, I guess we have two more things here maybe that we want to talk about, and then we'll call it good. Okay, and we'll do the fun sheet. But let's talk about what it means for a matrix to be squared and what it means to take a matrix times itself many times, right? And so can we do that? We can do that as long as we have a square matrix, all right? So a square matrix, and this probably makes sense to you. So a square matrix, right, is a matrix that has an equal number of rows and columns. And the reason we need a square matrix to multiply it times itself a bunch of times is because once you multiply two matrices together, right, that can change. Oh, whoa. Let's snooze with that real quick. That can change the size of the matrix, but if we have a square matrix, it'll stay the same size. So a matrix with an equal number of rows and columns. Oh my goodness, come on, stop. All right, so if we have an equal number of rows and columns, okay? If we have that, then I'm going to just go ahead and we'll just write this down, that what does it mean to take a to the kth power? Well, I'm just going to take a times a times a. We'll go ahead, and this is some new notation, maybe not really new, but you have to be a little bit careful because we can't always assume, but that's what we're going to define a to the k to be. As long as a is square, right, I can do this, but there are k copies of this matrix. Okay, that's what it means, where k is a positive integer. Okay, so we need to make sure that we have a square matrix to do that, and that's what we mean by taking a to the kth. And we said that's true for any k as long as k is a positive integer. Well, remember, integers do include 0. So what does a to the 0 mean? That means it's what we call the identity matrix, and I believe we get to this in the next section. So spoiler alert, an identity matrix is a matrix with ones along the diagonal and zeros everywhere else. So you have 1, 1, 1, dot, dot, 1. Oh, that's horrible. And then zeros everywhere else. Oh, that's really, really bad. Okay, all right, cool. So I think I'll let you, there's a couple more examples in the book. I would like you to look at those too, please. So look at, I would copy example 1.27. I don't know if you have to copy that into your notes. You might copy some of those into your notes. I think the ones that are kind of interesting, if you look at F and G, I would like you to particularly look at F and G in your notes there. Those are kind of interesting ones. And they talk about what does it mean to kind of do stuff that we would do in algebra, but instead of having variables, what would it mean if we had matrices there, okay? All right, you guys, I'll post the homework up on the announcements. I'm also on the announcements going to let you know when the first test is going to be. And again, I'm really, really sorry that I wasn't able to be there today, but I will see you for sure on Tuesday.